how did you initially make this discovery that essentially, like, the high level view is you're positing that where the Earth sits in the Milky Way galaxy is directly responsible for geological climate change on Earth?
That's true, but that came later.
Okay.
So it actually, I mean, the initial thing has to do with solar activity.
Okay.
There were some ideas that if you have change in solar activity, then there were some changes in climate. It's an old thing, and it's something people have been speculating.
What? The sun affects the climate? Who would have thought?
Yeah, but I mean, you will be surprised how little effect it is believed to have in the what you call the International Panel on Climate. But anyhow, there was these ideas that when you have a change in solar activity, there seems to be changes in climate if you go back in time. So it's an old idea. And I was at the Meteorological Institute at that time, and I was looking for something interesting to do. And when I heard about this agreement between solar activity, I thought that if it's going to work, the most effective way would be if solar activity somehow changes the Earth's cloud cover. So that was the idea. I mean, you probably know that clouds, they have a big impact on the temperature on Earth. So
because they reflect sunlight?
They reflect sunlight. So they do two things. They both reflect and they also keep the heat. But the reflection is what, wins. It has the largest contribution.
So what made you think that the solar activity had to directly affect cloud activity?
Well, the idea was immediately that it had to be with cosmic rays. So cosmic rays, what are they? They are particles that comes from our galaxy, our Milky Way. They're very energetic.
Bless you.
They're very energetic particles, and they shower the Earth. And the idea was that I remember when I was in high school, I worked with what's called a cloud chamber. That was what we saw just before, a cloud chamber where you have particles where you can see the streaks of the particles. So just like you have an airplane, you can see in the sky, you can actually see when the charged particles go through in a cloud chamber. So what happens is that you have a supersaturation, typically some alcohol, and then each little charge, it condenses this liquid, and you see these small droplets. So that's why you see these streaks.
Okay.
This is what you see here.
Okay. Oh, this is the cloud chamber.
So this is a cloud chamber, and you can see these long streaks, and these are what we call these are cosmic rays that are entering through a very thin layer where the cloud chamber is active.
Oh, wow.
So, and the very long straight streaks, these are called muons. These are actually produced in 11 kilometers or 13 kilometers or 20 kilometers, and then they move down through the atmosphere. So you have a collision just like with billiard all the way down through the atmosphere. I mean, we can actually...
Wow.
You can see it if you look at... if you take the one before, number 5, yeah. So what you see here is from 25 kilometers and down through the atmosphere. You see one particle is coming in with a very high energy, and then you are producing a shower of secondary particles.
Wow, it's like a shotgun blast.
It is.
And these are a cosmic ray.
Yeah, it's called a ray because when they first discovered them, they didn't know really what they were, but they are particles.
So it's a sun particle.
It's not from the sun, it's from our galaxy.
From the galaxy. Okay.
So it's called galactic cosmic rays.
Okay.
So, and the thing is that if we go outside, when solar activity is changing, it modulates how many of these particles enters into the atmosphere.
Okay.
So solar activity can sort of regulate the number of particles.
So like solar wind, if we have lots of solar wind around like the Van Allen radiation belts, it can deflect lots of these cosmic rays away from the Earth.
The solar wind, yes, exactly. It sort of screens against these cosmic rays, so they're just sort of scattered out into space. And these changes in cosmic rays are some of the largest that you have with respect to changes in solar activity. So you can have maybe 10, 15, 20% changes in cosmic rays.
And what is so unique about these particles that we call cosmic rays?
These are mainly protons, meaning that they are the simplest element that we have. So there's hydrogen, the core nucleus of the hydrogen.
Okay.
And the origin of these particles, we can talk about that, is actually when big stars explode.
Oh.
So these are what we call supernova explosions. And when you have a supernova, you have this expansion of a shock front. And then these charged particles can get accelerated to enormous energies. So you can say that this works as a cosmic accelerator that makes these particles, they give them enormous energy.
Wow, and it just blasts them outwards.
Yes.
Through the rest of the Milky Way.
Yes.
And it hits.
So it sort of fills the whole part of our Milky Way, and where we have the solar system, the particles, they enter, and solar activity can then modulate it.
Okay, so these cosmic rays, how do they make clouds?
That is then the thing. In order to look how...
And you didn't know they made clouds. You had to figure this out.
I had to figure it out, yes.
Right, okay.
So if we look at number 14, I think, if you look at... Yeah.
Okay.
So if you look at the left-hand side, you can see you have free charges which are made by cosmic rays, and that stabilizes very small molecular clusters, and they're only about 1 to 2 nanometers. A nanometer is 10 to the minus 9 meters. It's so small you cannot see it. So it's only, a few molecules that stick together, but because of the charge, they are stable, so they don't evaporate again.
Okay.
And the idea is that if you produce more of these small aerosols, then as a function of time, they grow because they take up more gas, and you can have they collide, so they sort of, stick together. And then at some point, they are, about 50 nanometer. And then you can call them cloud condensation nuclei, because in order to produce a cloud, it consists of cloud droplets. You have to have a surface on which water vapor can condense.
Okay.
So,
and those are the cloud droplets.
And then become cloud droplets, and if you have sufficient of them, you have a cloud. Okay. So the idea is that if you now have more cosmic rays coming in, then you are producing more of these cloud condensation nuclei. If you press,
and so
just press one time down. Yes. So what you see up here is an indication that if you change the number of cloud droplets, you are changing clouds. What you see up here is a region from a satellite image where you have low clouds, and then you can see that there are these stripes, and these are ship tracks. So what happens is that the ship is pumping out, particles from the engine.
Yeah.
And then that goes into the clouds, and you can see it changes the clouds.
Wow. Like cargo ships in the ocean.
Yes. So they change the clouds. So it's just like, airplane, you see it, but here it's in low clouds. So what it shows is that if you can see it here, if you change the number of cloud condensation nuclei, you change cloud properties.
Whoa. So what are the differences between this left and right? By the way, for people that are just listening, I highly recommend you watch this on video. either on YouTube or Spotify, because this is going to be a highly visual episode. So what are the differences between the left and the right here?
These are just different cloud scenes where ships have been sailing. So, and in the one in the right, you can actually see that it is really clouds that have been changed. So the idea is that if the cosmic rays can do this systematically all over the Earth, because they are omnipresent cosmic rays, then it would be a very effective way of regulating the Earth's climate.
Wow. And you were the first one to posit this.
I was the one that said that there is this connection, and that seems to be real.
And what has been the feedback from the scientific community on this specific connection that you've made here?
I mean, I did it in 1996. There was a conference in Birmingham where it was presented the first time, and a newspaper, a Danish newspaper, put it out. And it I mean, before that, nobody cared what I did. After that, it was completely crazy what happened, and we got an enormous reaction and very aggressive reactions. I remember coming back from the conference, and there was a headline saying, strong UN critique of Danish researchers. That was the International Panel on Climate, which is under the UN, saying that what we had done was naive and irresponsible.
Naive and irresponsible. Did they disprove the connection that you made between?
No. Nobody has disproven anything.
Okay.
So,
but nobody has said that the connection that you've drawn here with your evidence is everyone said that it's legit. No one's proven that it's.
Let me put it this way. When we started, everybody was saying that we don't know any known mechanism that can do this, so it cannot be true. I think now the next step is that they're saying, okay, maybe there is an effect, but it's not important. And the final thing is that they say that this is what we all said all along.
Now, when you first came out with this, did you publish it to like a scientific? I don't know how that whole process works. When you're a scientist, you put it published and all that.
Everything I've been doing is going through the normal way of doing things, which is to find the results, write them up, and publish them in good journals. So it's what you call peer reviewed.
Peer reviewed, yeah.
So there's no guarantee that things are correct, of course, but someone has seen it through and says that, okay, let's our colleagues consider what you're doing.
Right. Okay. So you made this connection with the cosmic rays being specifically associated with cloud formation.
Yes.
Now, how do you extrapolate that into a correlation of the cosmic rays being primarily responsible for the change in the climate on Earth?
Well, the idea is that if you change the clouds, you change the amount of energy that goes into the Earth's system. So if you have a systematic changes in clouds, let me
ask you this. Sorry to interrupt, but is it accepted with the mainstream that clouds are primarily responsible for the climate?
Well, it is mainstream that clouds are important.
Important.
Yes, and another thing that is extremely, everybody knows that clouds are the the most difficult subject in all climate modeling, because it's so difficult to model cloud processes.
Right.
So if you have a systematic change in clouds, and this is well known, I mean, if you look at marine stratus clouds, which are the low ones that you always see when you fly over the oceans, these endless scenes, if you change that just by 1 or 2%, it is similar, to all the greenhouse gases. The change in greenhouse gases, so it's 1 or 2 watts per square meter. So it is really important.
The low clouds.
Yes. marine clouds. Yes.
Interesting.
So, I mean, if you show slide 13, you can see the figure that actually started the whole thing. So, what you see here is since 1983 until 2005, and you can see the red curve is the change in cosmic rays over the until 2006.
Wow.
And the reason that you have this change is because of solar activity. So this is the 11-year cycle that you see. So solar activity is modulating the amount of cosmic rays, and the blue curve, that is actually low clouds over this period. So you see there is a beautiful correlation, but it doesn't mean that we understand why it's there.
Wow.
So
that is amazing.
That's how it started.
So for people that can't see this graph, from 1985 to 2005, the correlation between cosmic ray activity and low cloud coverage is spot on. Like it tracks perfectly throughout that whole time. So let me ask you this though: how do you track the cosmic ray activity going back that far?
I think since the beginning of the 1950s, you have been measuring systematically cosmic rays with something called neutron monitors.
Wow!
So
we've had this since the 50s.
Yes, in the 50s. Yes, it was an American actually that started this part. Neutron monitors are operating, and they're measuring all the time. So you can see changes in cosmic rays.
Past 1950, we can't go any earlier than that as far as measuring cosmic rays?
We can.
You can?
But it has to do with, you have to do it indirectly. So we call it proxies. Mm-hmm. So when cosmic rays comes into the atmosphere, they are producing new isotopes. That is new elements. You know carbon-14? You've heard about carbon-14?
Right.
And carbon-14 is produced by cosmic rays. And so then you can imagine that you have this carbon is slightly heavier than carbon-12. So it goes into, it sticks to oxygen. So you have CO2 with carbon-14, and it goes into leaves and goes into a tree. And then in the tree rings, you can measure the amount of carbon-14 relative to carbon-12 in all the tree rings.
Oh, wow.
And if you measure that, you can then say something about how solar activity has changed back in time. So it's something you have to take into account also when you're doing, archaeological studies. You have to take into account that solar activity has been changing. Otherwise, you will get completely different ages.
I've seen models of the climate, the Earth's climate going back we've pulled them up on this podcast going back 50 million years. How do they accurately figure out what the climate was 50 million years ago?
There are indirect methods, and one is to use what we call oxygen 18. It's again isotopes, but
this is the cores, the ice cores, and all that.
Ice cores only go back 800,000 years.
Oh, really? Okay.
And they're best 100,000 years back, or a little more. But if you want to go even further back, one thing is that you can take some, it's interesting because you take some animals that lived, some shells.
Fossils?
Yeah, fossil shells. So in the shell of the fossil, you measure how much oxygen 18 there is relative to oxygen 16. And that says something, it says something about how hot the water was when the shell was formed. So you can go in different layers of the Earth and find these fossils and measure, and that gives you a proxy of the temperature as you go back. And I have things I can show you.
Oh wow, that's amazing.
Yeah,
I've seen different things I've had geologists show me different layers of the sediment where there's this black matte layer that correlates to like, what was it, 12,500 years ago or whatever, during this Younger Dryas event.
Oh yeah, yes.
And lots of people believe that, or speculate that there could have been like this crazy asteroid impact or comet impacts throughout the Earth, that when we passed through a specific cycle or when the Earth passed through a specific zone of the universe or whatever, there was like high asteroid or comet activity that could have been responsible for that, like a mass extinction event or something.
Yes, that's. I heard that too.
Mm-hmm. And then like allegedly like everything was flash frozen, and then everything was like got really hot, and then there was like a flash freezing event where like the sky blacked out and everything got super cold.
Yeah.
Mm-hmm.
It makes a big change.
Mm-hmm. What do you make of that theory?
I think it's interesting, and you try to find the evidence in the ground, so that's fine.
Mm-hmm. So, what's next as far as your discovery and in the process of you making this discovery and presenting it to the public? You're now showing people that, and you've got papers that prove that this specific activity of cosmic rays correlates to climate going back to at least 1850 or 1950.
It correlates, yes, and the big problem. I mean, these are correlations. Mm-hmm. That's what was the start of the whole thing. So you have to. I mean, because there's a correlation, and this was something that people were telling me all the time, that just because you have a correlation, that might not be causation. Mm-hmm. So the idea has been to try to figure out how to, prove or investigate what the mechanism could be, because you have to, go further into the problem. And very early, I realized that we had to do some experimental work. And around 2004, and maybe even earlier, I built a laboratory where we could make this type of experiments. If you look at, I think it's slide, it's a 16. Can you see that? You can see here, these are all the places that we have been doing experiments.
CERN, the DTU National, this is the Danish National Space Institute?
Yes. And
at the Astrid Accelerator? I haven't heard of that one.
No, it's in Aarhus. It's in Denmark.
Oh, also. Okay, yeah.
And then you have CERN in Geneva.
CERN, yep.
And then at some point we went 1.1 kilometer underground in a mine because we wanted to avoid cosmic rays. And you have to go that far down in order to get the cosmic ray intensity down by more than 1 million.
Really?
Yes. So they are very, very penetrating. I mean, as we sit here...
How deep again?
1.1 kilometer.
Wow. As we sit here, we're getting pelted.
Pelted, and they go right through us, and there's nothing, spectacular as such, because this is happening ever since, for the last 3 to 4 billion years for all life. So it's part of our environment.
Okay. So what was going on at CERN?
At CERN, we did some pilot experiments. There was a project called the Cloud Project that was built at some point. I was part of the Cloud Project in the early stages, but then I switched to our own. We did experiments where we actually showed that, yes, there is a microphysical mechanism. If we increase the ionization in a large chamber, we can see that we are building small aerosols. So we can measure that, and we could sort of document it. I think if you go to...
so that's the reason for going so far underground, is to spray your own cosmic rays. At your experiment, you have to eliminate all the cosmic rays coming out.
That was the one in Bulby, yes.
Right.
But the one in the DTU, the National Space Institute, there we have some gamma sources outside the chamber, and then we have some, we call them, we have some LED, walls that we can move and then we can increase the ionization in the chamber, and we can turn it down. If you go to the next slide, I think there you can see one example of such an experiment. You have cosmic rays, or this is actually ionization, that increases along the bottom axis, and then you can see as we increase the ionization, we actually produce more of these particles. So it's just an indication that there is a microphysical mechanism that links the two.
So Earth's climate goes up and down,
Yes.
and constantly throughout history.
Yes.
And we've seen this just from the graphs that we've already seen before that just show the climate. I mean, we have like the medieval warm period. We have, it seems like right now, just based on the last couple million years that we've tracked, that right now it's cooler than it's been on average over millions of years, over the last at least 5 million years, right?
Yes, it is much cooler. If you go back 50 million years, I mean, Earth might have been 10 degrees warmer than now. So you had, palm trees in Antarctica at that time, and baobabs trees and so on. I mean, so it really is something that here we go 3 million years back. So, but there you can see there has been a steady cooling over the last few million years.
Yeah. So this blue one is. What is the blue one record for?
It's more ice.
More ice.
More colder. When it goes down, there's more
atmospheric CO. So that's the question. Is there a correlation between the temperature and the atmospheric CO2?
In the ice ages, yes.
In the ice ages?
Yes. I mean, you see a very clear correlation. The thing is that it's probably CO2 that is reacting to the temperature and not vice versa.
Oh.
So you can actually see if you make, if you look very closely at the data, you can see that the temperature changes first and then the CO2 changes. This is something, it's commonly known.
So in the ice ages, it was very low CO2.
Yes, and yes. It was so low that, it was a problem for plants at that time. That's also why instead of C3 plants, you developed the C4 plants. They are much better at taking up CO2 than ordinary plants. If you go too low with CO2, all life dies.
Interesting. Right. Yeah, no, I knew that. But so that what you're saying, which is counterintuitive to mainstream knowledge, is that, or mainstream, whatever the narrative is that the CO2 reacts to the climate. So if it's a really hot climate, the CO2 will go up.
Yes.
Got it. So why do people say it's the opposite?
It's because here, in the modern period, we are burning fossil fuels. So we are putting in more CO2, and CO2 is a greenhouse gas. So so by putting in more artificially, we can of course raise the temperature a little bit because of that.
Oh, okay. Okay, so you're saying that the man-made carbon dioxide that does go into the atmosphere every day, that does have a little bit of an effect on the overall temperature, but it pales in comparison to what these cosmic rays forming clouds can do.
Yeah, on the longer time scales, as I can show, is remarkable correlations on the long time scales, yes. But also, if you look at you talked about the Little Ice Age.
Right.
That is a period where you had very few sunspots, so very little solar activity. So therefore, there was much more cosmic rays coming in during the Little Ice Age, and that is a beautiful correlation.
So that's an interesting thing that you said there. That's kind of hard to try. It's kind of counterintuitive. It doesn't really, until you really understand it, right? You're saying that the low amount of solar activity equals more cosmic radiation.
Exactly, because the sun forgets to throw away the cosmic rays, right?
Right.
So when when the sun is at low activity, the cosmic rays don't get so much resistance in going in.
And more solar wind, more sun activity, the least amount of cosmic rays.
Yeah, and warmer climate.
And warmer climate.
Yeah.
The more cosmic rays we get, the more clouds we get, and the cooler the climate.
Yes. And it's also interesting. I mean, when you had the little ice age, you had. When you had bad weather and so on, you at that time they believed it was because of witchcraft. And it's amazing because so many women were burned at the stake because of if you had a bad storm. They had to find the culprit, and that was witchcraft. So at that time, many thousands of women and men also were burned at the stakes because of bad weather. I mean, there are some storms. There's a famous thing with a Danish.
Listen a little closer to you.
Yeah, there was a Danish princess that was going to be married to an English king, and they were trying to sail from Denmark to England, and they were hit by a bad storm. And because of that, the king thought that it was witchcraft, so they actually executed a large number of people because of that storm.
Jesus. Yeah, the things that human beings have done in response to weather or to try to make the weather change going back is just, the Mayans would sacrifice people to appease the rain gods, for crops and stuff like that. So you say that the magnetic field of the sun has more than doubled in the last 100 years. Is that right?
There has been an increase in solar activity over the last 100 years, yes. I can't remember. There was a paper at some point where they said that the sun's magnetic field has more than doubled over the last 100 years.
Do we know why?
No, but I mean, it has to do with solar activity, and solar activity is not something that is well understood. Mm-hmm. So, for instance, when we say that there might be a solar minimum, that is a very low solar activity in the future, it is very uncertain because we cannot predict these things very good. Mm-hmm. But we know that there has been a large number of what we call minima in solar activity. I mean, 6 or 7 times during the last 10,000 years. Mm-hmm. And each time you have a very cold climate. I mean, I can show you a very beautiful. If you look at number 10 of mine, let's see. No, was that number 10? Oh, sorry. It's number 8.
Number 8.
Yeah. So what you see here is the last 12,000 years. If you look at the bottom figure, and the black curve is actually an expression of climate, and it's an indirect way of getting the climate. It has to do with icebergs that moves over the North Atlantic, and when they move over the North Atlantic, when they melt, they have a lot of small stones in the ice that then fall down on the bottom. And then you can drill up these ice cores, and then you can see how many small stones there are as a function of time. And that says something about how many icebergs have moved over the North Atlantic.
Oh, wow.
And that's the black curve. And the blue curve is changes in cosmic rays over that period.
Oh, wow. That's incredible. So, and explain what you are saying about when it comes to the Milky Way galaxy and where our solar system is currently in the Milky Way galaxy is constantly changing, right? And is it our solar system goes around the whole Milky Way galaxy, does one rotation in what, like 100 and something, 200 million years?
Yeah, 230 million years.
230 million years. We make a full rotation around the Milky Way galaxy.
Yes.
That's crazy. And each rotation, we go in and out of the arms.
Yes. And the arms are not sort of material arms. It's actually a wave phenomena on top of all the stars that are moving around. And the reason that they look more bright is because that's where you make a disturbance, and that's where you have the star formation. And that's also where the young stars that are large stars are, and they're much more bright. So that's why you see the spiral arms as bright arms. Mm-hmm. And we are moving in and out of these regions. And when you have more star formations, that's also the places where the large star explodes. And the large star that explodes are the ones that produce the cosmic rays. So when you are in a spiral arm, you get much more cosmic rays, and the changes are maybe 300% change in the amount of cosmic rays.
Wow!
And then opposite, when you go between spiral arms, then.
Can you show? Do you have like an image of this that we can see to give a better understanding of it?
If you look at number 31.
31. So these bright spirals that we see, this is where you're saying a lot of the new stars are born and dying?
That is where the new stars are born. A lot of stars is born, and new stars are dying. I should say that I work closely with a guy called Nir Shavib. He's a professor in Israel. And I worked with him for many years. He's the one that took up this idea. So he's the one that he made this idea that when we go through spiral arms, it should be important for climate on Earth.
Really?
And each time we are in a spiral arm, there seems to be a glaciation on the Earth. So it's a cold climate. And I can show you.
When we're in the spiral arm, it becomes very cold.
Yes, because you have more cosmic rays, and more cosmic rays mean more clouds, and clouds are cooling.
Right. Wow. Okay. So what is it about? Why are more stars being born and also exploding in these spiral arms?
It's simply because in the Milky Way galaxy, it's like a disk, and in the disk there's a lot of gas in the form of hydrogen, and hydrogen is the basic element in stars. So what is happening is that you have sort of a disturbance along the spiral arms of the gas, and that makes the gas sort of collapse. And it becomes more and more dense, and then at the end, it ignites the stars.
Whoa!
And when you ignite the stars, you are actually producing a whole range of different size stars, and some of them will be the heavy ones. That because they are heavy, they burn very strongly. And they don't live very long. So you only live maybe between 3 and 15 million years. And that's a short time compared to the rotation. So the very, very bright stars, they are typically have a short lifetime in close to the spiral arms. And that's why you get more cosmic rays in the spiral arms.
Wow. That's so hard to comprehend, just the scale you're talking about. Like you're able to explain what's happening chemically within the entire Milky Way galaxy. It's so crazy. And so where is on this giant diagram of the Milky Way galaxy, where is our solar system roughly?
Well, you can see there's the sun location with the star in the bottom. So we are about 1 or 2/3 outside. And we are actually moving around the galaxy, the center of the galaxy, within about these 240 million years, and then we go in and out of the spiral arms.
So, let me ask you. This might be a dumb question. This might be the might not be the right person to ask. But are we moving away from the center of the Milky Way galaxy consistently, or is it staying about the same?
It's staying about the same. I mean, it's not a perfect circle, of course.
Right.
But because there are some disturbances, but it is more or less, for all practical, we can call it a circle around the galactic center.
Is it?
And the sun is what we call a disk star. and all the disk stars are moving around the galaxy.
Why is it a disk star?
It means that it's because when you have star formation, many times they are born in a cluster. So you have many stars that are bound together by gravity. I mean, do you want to see this process?
Oh yeah, of course.
Okay, then go to number 57. It's simulation.
Okay.
So you can see how.
Perfect. So you're talking about like binary star systems?
So here you have a gas cloud, and it has been disturbed, and now it will start collapsing, and you will see you will have star formation, and you will produce a large number of stars. You can see a lot of. So these small white is actually stars that are igniting.
Oh wow!
So,
what is that stuff that's like popping out of them?
That is gas that is being accelerated and thrown out. And I even think in this there is a supernova going off. You can see that they throw out some stuff.
Wow.
So at this time, these stars are all from the same cloud. So you can say all these stars are siblings in the sense that...
in the same cloud.
Yes. And then what happens... I mean, at some point, I think it ends, you can sort of zoom out a little bit and you can see that you have what we call an open cluster. This is an open cluster of clouds.
So what we're looking at right now
is star formation.
This is star formation, right?
Yeah.
But like on the, can you give me like a relative scale?
Yeah, it's probably 150,000 years or something like that.
This is about 150,000 years. And how big are each of these stars that we're looking at compared to like our sun?
They are probably, many of them are smaller and some of them are bigger. They form after, I mean, it's always formed, there you had a supernova going off actually. But you see, it's like this is what we call an open stellar cluster. And the reason I'm showing that, it's because I have been using open stellar clusters to go even further into this problem on the long time scales.
Superstellar clusters.
Open stellar clusters. Open. Yeah, because you remember we started asking the question why it's a disk star.
Exactly. Yeah.
So here you have stars which are part of a cluster. So what is happening is that they sort of move in between, and there might be some disturbances, and then the stars they sort of fall off. So the gravity can no longer keep a star bound, and when it falls off, it becomes a disk star. So our sun probably also was born in this way.
And then it eventually just like drifts out.
And it eventually drifts out. Yes.
So there could be no life in one of these clusters. It's too hot, too many stars.
Well, it's very young at this point, right? So it hasn't had time to evolve. But I mean, there probably will be planets and so on around some of these stars. Yes.
Inside this cluster.
Yes, there will be the formation. I mean, now we know that nearly all stars have planetary formation.
Wow. So, that is bananas.
So, if you go to number 34, what I'm showing you here is the number of, if you in the middle there, in the middle of this circle, that's where the solar system is. And after these dots is an open stellar cluster. So these are open stellar clusters. That is a group of stars, and the color, it says something about how old the cluster is.
Oh.
And you can see most of them are about 100 million years.
So the dark purple at the bottom is how old?
100 million years.
And what's the red?
And red is 1 billion years.
1 billion.
And you see there's very few of the old ones. And that's
not many old ones.
No, and that's because they have evaporated. So all the stars have been falling off, so they no longer exist.
So they exploded?
No, they fall off, so they are no longer a cluster. So it drops stars, and each time you have fewer and fewer, and in the end, there's nothing left. So they're all becoming disk stars.
Okay, I see now.
So, and in this plot here, there is information about star formation over the last, for instance, 500 million years.
Mm-hmm.
So if you move to the next slide, you will see a reconstruction of the number of supernovas over the last 500 million years.
This is 500 million years right here.
This is 500 million years, and you can see that the changes in supernovas or the supernova activity is almost a factor of 3. So for 300 million years ago, there was a lot of cosmic ray or a lot of supernovas going off.
And you're measuring this directly by the proxy of the cosmic.
This is measured by these open stellar clusters that I use the information in them to say how many stars were born at a certain time. When I know how many stars have been born, I know what fraction have been large stars, and then I know how many will explode and produce cosmic rays.
Okay.
So it's an indirect way because we have no way of doing it.
Got it.
But I mean, it looks very.
So you can use basically Earth's climate history to reverse engineer this stuff right here.
That's a good question. What you have here is only astrophysics.
Right.
There's nothing. The top bar you can actually see when there is glaciations and when it's cold. So you can see over the last. In the first part, you have the first 30 million years. You have a large glaciation.
Lots of supernovas.
Lots of supernovas. And if you go 300 million years back, you can see there's glaciations, severe glaciations again. And there seems to be a very nice correlation with this figure as you go back in time.
Wow.
But let me take it even further. If you take the next slide, what you have here is only 200 million years. And what I've done here is I've used a proxy for temperatures going back in time. Remember we talked about these shells. I think they're called brachiopods.
Fossils, like fossils?
Yeah, these are fossils. And then you measure the amount of oxygen 18 relative to oxygen 16.
And you can figure out the water temperature, right?
And that gets you the water temperature. And this is what you see with all these dots. Each of these dots is a fossil.
Okay.
And you can see the red curve is the change in supernovas. And you can see there's a beautiful correlation between the two.
Oh, interesting.
And when there's many supernovas, you can see that it's actually quite cold on Earth. And when you go back, for instance, 50 million years, it was much, much warmer.
Wow.
And also, I think it's quite interesting because if you look at just the last 30 or 40 million years, you can see there is a sort of a minimum at around 30 million years. That minimum is also shown in the data for the temperature. So there is this. I mean, it's actually a quite beautiful correlation even on these time scales.
Have you noticed any sort of pattern in this activity? Like every, 10 million, 20 million, 50 million years, is there? I mean, obviously there must be some sort of a relative period of time in between each one of those arms in the Milky Way galaxy, right?
Yeah, yes. And this is, I mean, if you look at the beginning, that's because we just passed the spiral arm. If you then go back and you see that there is a minimum around 140 million years ago, this is another spiral arm that we go through. So you can actually see the spiral arms in the data.
Wow.
And when we go through a spiral arm, it's actually colder. When we are in between the spiral arms, you can see it's
hot like a desert.
Yeah, it's really, really hot. So that's just...
and I'm sorry, can you show one more time where exactly we are in the spiral arm?
We are where you see is a 0.
Yep.
So that's up top.
Okay. Yep. On the top right is where.
Top right, yes.
So are we in a spiral? We're not in a spiral arm right now.
We just moved through a spiral arm, and we are experiencing over the last 30 million years, we have had a glaciation. A glaciation means that we have ice sheets on Earth, and Antarctica, it glaciated about 34 million years ago.
So that's when Antarctica was formed, about 30 million years ago.
The ice sheets.
The ice sheets.
Yes. So 40 million years ago, or 34 million years ago, that's when that happened. So the ice sheets, they sort of formed.
So when the dinosaurs were walking around, there were no ice sheets down there?
When the dinosaurs walked around, they disappeared around 65 million years ago, and that was very warm. There was hardly any ice at all.
Wow.
But of course, I mean, the first dinosaurs came 250 million years ago, so
right.
they had a long period on Earth.
Right.
But in the end, there was no ice.
So we're technically in a glaciation period right now, and we're exiting it.
We are in a glacial period, yes.
And we are about to get very warm. Not probably, I mean, we're talking geological timeframes here, but...
we will go in through, in maybe 30 million years.
In about 30 million years, it's going to get very hot.
The weather forecast for 30 million.
And so how long do you think it will take before like the South and North Poles are completely melted?
That's a good question. I mean, it comes... I mean, you can see here it's over some millions of years, I guess, that you have a change if you look at it.
Yeah, so...
And also, I mean, when you are, if you look at the 50 million years when you don't have any ice sheets, the sea level is of course much higher.
Right.
So, and you have the continent are flooded. So the U.S. was flooded. Parts of the U.S. There was no Florida. Florida was underwater.
Now there was a moment in the documentary that you guys did where they were like looking at the sediment layer near the Dead Sea. Is that right?
Yes.
And there was like some cliff sides near the Dead Sea, and you guys were studying that. What exactly were you guys looking for there?
It was just an illustration of past climate that you can see in these sediments and how it's changing. And I think there's someone who has studied it in more details and showing that there are some correlations with climate in the sediments.
Now, is there any specific correlation between supernova activity and like biological life on Earth?
Yes, and that's one big part of my work now that I've been working on.
And is that all tied back to climate?
It ties back to climate because the temperature changes that you have here is maybe 10 degrees. Global temperature. Remember, we are talking about maybe 1 degree with global warming, but 10 degrees. It's so big that it will have impact on climate.
10 degrees.
Yeah, these changes are just huge that we are talking about, and I can show you. I mean, I think it's completely fascinating with this. So if you go to 37, so this is just to say that climate is quite important because at any time here on Earth, nutrition has been a limiting factor.
Yes.
So nutrition, that's phosphor, iron, and nitrogen, and so on. It's all things that life is needing. And there is this, if you have a certain bioproduction, that is, you have life, then life would rather uptake carbon-12 than carbon-13. 1% of carbon is slightly heavier. It's a stable isotope. But carbon-12, and this is important because it gives us a way of saying how much biomass there was on Earth at a certain time. So when you have sediments, and you can have inorganic sediments that fall down on the bottom, and that makes all these sediments that you see, we'll see them just in a second. Mm-hmm. Then you can imagine if you have a large biomass, that means that there's more carbon-13 in the oceans than if you have a small biomass. So by measuring the ratio between carbon-13 and carbon-12, you can say something about how much biomass there was on Earth at a certain time. If you go to the next slide.
Wow.
You can... Is that the next one? Oh, it's just... Yeah, one more time. Yeah. So this is the Grand Canyon. So the idea, what you see here is all these layers are past times where you had an ocean bottom.
Oh, wow. Okay.
And then you can, geologists has then gone and measured this carbon-13 relative to carbon-12. And that estimate the fraction of organic matter that is buried in sediments. So this measure with the isotopes, it unlocks how much organic material there is, and that is how much life there was in the oceans at a certain time.
Oh, wow.
So if you go to the next slide, and so what you have here is my reconstruction of cosmic rays over the last 500 million years. And you can see there's some different curves, and these are different data bases that I have used, but they all show more or less the same thing.
Okay.
And that is the change in cosmic rays over this time. So what you see here has nothing to do with the Earth. It is astrophysics, pure astrophysics.
Pure astrophysics.
So if you press the bottom, you will see the change in. This is the fraction of organic matter in sediments over that period of time, and you see a remarkable correlation.
Whoa.
Holy crap.
That is wild.
So
the more of this astrophysics activity that we get, the more organic matter we get.
Yes.
That's correct?
Yes. It's the fraction of organic matter in sediments. And the idea is, if you press one more time, I think that something will come up for explanation there. So if you have a high cosmic ray flux, you have a larger bioproductivity, and therefore also a larger fraction of organic barrel into sediments.
So the hotter it is, the more organic matter you get.
The colder it is.
The colder it is. So the higher cosmic rays... Okay, yeah, I'm thinking when the word ray breaks my brain. I think sun rays.
Yeah. But it is this sign thing is problematic. But it seems as if nature can figure it out.
So the lower the temperature, the more organic matter.
Yeah, and why is that? It's because that when it's cold on Earth, you have a larger temperature gradient between the equator and the poles.
Okay.
There's a larger temperature difference
between the equator and the poles,
and that means that you have stronger winds. So if you have stronger winds, you have much better circulation in the oceans of nutrients. So then you can deliver nutrients to the life, and that's why when you have a colder climate, you can get more. It helps delivering the nutrients.
So even though it would probably be less organic matter on land, though, right? Because it's very cold, and there's not much. There's no vegetation.
It's something I've been working on. It's not published, but it seems as if it's completely opposite on land.
Wow.
So,
So would it be so if it's a very warm climate and it's lush on land and fertile and lots of life, that would mean it would be the opposite under the oceans?
Yes, because then you have a smaller temperature difference between the equator and the poles. There's not much mixing in the oceans. It gets much more layered, so you don't get the nutrients circulated.
That is wild.
So this, this I think this published it in 2021.
Mm-hmm. So those layers that you're measuring, the difference between carbon-12 and carbon-13, that's specifically for the organic material, the organic mass that's under the oceans.
Yes.
Now, how do we measure what's above the oceans?
We can't really measure it that the same way.
No.
So that's a problem. So what I've been doing is trying to model it based on photosynthesis, and you have how much energy that goes in. You have to see how much CO2 there was in the atmosphere, how much oxygen there was in the atmosphere, and how much water was available. And you put all these things together, and you can try to at least simulate the organic amount on land.